A-level capacitors. We're looking at what they do, what they look like, and understanding their behavior. So let's do that then. So what do capacitors actually do? Well, what they do is they store charge. You place a PD across them, you build up a charge on them. As a consequence, they store energy. So a capacitor is a device which stores charge, and as a consequence of storing charge, it's storing energy. And from your work in electricity, from your work on electric fields, you would understand that in order to move the charge, you've done work, so energy has been transferred or converted in doing that work, and the energy is being stored in the electric field. So that's what capacitors do. What do they look like? You might have seen some before. Here are a variety of different capacitors. You can see that they have ratings on them, some of them, 1 kilovolt, 500 volts. This is your maximum working voltage. This is the maximum PD that you can place across your capacitor without doing damage to it. This is the sort of capacitor here that you might expect to see in the lab, the sort of thing that you might be doing your required practicals with. But there's a variety of different appearances, a variety of different capacities of capacitances. And here are just some commercially available capacitors that you might see. So, having seen what they do and what they look like, where might you find them? Well, all over the place really. In any electronic device at all, you will find capacitors. So, you have them in computers, you have them in, this is a home security system, and the capacitor is used among other things for the timing circuit. So that's what I've got this here for. You might know that when you put in your key code to arm the alarm, you have a period of time from that point to leave the building or leave the room until the alarm arms, and that timing is using a capacitor. Equally, when you come back into the room and you set to disarm the alarm, you have a period of time from the sensors detecting you to put in your key code to disarm the alarm before the alarm goes off and calls the police or whatever it's going to do. So they are used in timing circuits. Here we have an example. It doesn't look terribly impressive, but this is an uninterruptible power supply. What this does is ensures that if there is any break in the supply, however small, the electricity supply, the IT systems connected to it can still function. So you would use this for critical IT systems, for national security, for databases that must be up 24/7, for the NHS, for example. Critical systems that absolutely cannot go down, you would use an uninterruptible power supply, and they use capacitors. This is a bit of fun. It's not one I would necessarily cite as an example in my exam, but you might have come across these bug-killing tennis rackets. They've got a 9-volt PP3 battery in the handle. They use the capacitors to build up a substantial charge, which when the bug completes the circuit between the two electrodes, the charge is released, a large current flows over a short period of time and kills the bug. They're also used for smoothing full wave rectified DC and for tuning circuits. We don't get into either of these really, but your television, your radio, your mobile phone, they all use tuning circuits. And essentially what's happening is your mobile phone or whatever is tuned in to a particular frequency. It resonates at that frequency. You get a maximum amplitude of potential difference or current in the circuit at that frequency. And in the case of the television, you can select that frequency. So you are tuning using a capacitor, among other things in that circuit. Again, we don't get into the detail of that. But using a capacitor in the tuning circuit, you're choosing the resonant frequency of that circuit in the case of your television, or it has been chosen for you in the case of your mobile phone. And when that particular frequency is detected, you get a maximum amplitude of potential difference or current in that circuit. And so you get your signal. Let me show you full wave rectification then, just because I've mentioned it. So if you take AC, so there we have potential difference against time. You could pass that through a single diode. I'll try and draw this as you're supposed to draw it. The convention for drawing diodes has changed from when I was at school. So pass it through a single diode. What you get then, you cut off, this is a perfect diode. Basically you cut off this bit. Now that's all very well, but you don't really want to lose that bit. So if you passed it through 4 diodes, oops, we're going to take our output across here. We're going to put our input across here. This is our AC input. So for our first cycle, that's a very poor diode, my apologies for that. So in our first quarter cycle, the current goes this way. Now we're going to have a diode this way so that it can't go in that direction. So the current goes this way, goes up here, can't go that way because the diode is reverse biased. So we have another diode here, which is reverse biased for this half cycle. So it comes up here, goes this way, can't go that way, can't go that way, comes down here, and then comes out here. So there we have our first half cycle. We have the current flowing that way. Then the second half cycle, current, instead of flowing that way, is flowing this way. So it comes this way, can't go that way, goes that way, can't go that way, despite my dodgy diode. So the current comes this way, up here, down here, out here, because it can't go that way. And so you have what comes out of here is that. So there you have full wave rectified DC. This is half wave rectified, because you're losing half the wave each time. You're losing this bit each time. Now, this is DC, but it's not very good DC, and it will damage your delicate electronics. So if you then pass that through a capacitor, which, as we'll see in a moment, is connected to a resistor, then what you end up with out of your full wave rectified, what happens is your PD across the capacitor rises and falls a lot more gently. That's not a very good one. That should come up there. So this is your smoothed DC. Now you don't need to know the detail of all this. Maybe I should have said that to start with. However, you do need to know that capacitors are used to smooth full wave rectified DC. So Excuse me. So that's one of the uses. So you've had several uses there. Timing circuits, smoothing circuits, uninterruptible power supplies, and all manner of electronics. So let's have a look at a circuit with the capacitor in it, and at the moment our switch is open. So if we close our switch, what's going to happen is electrons are going to be pulled off this plate because it's connected to the positive terminal of the battery, and dumped onto this plate because this plate is connected to the negative terminal. Now, of course, as soon as you remove an electron from here and you dump it on here, this plate is slightly more positive than it was before. This plate is slightly more negative than it was before. So removing the next electron will be harder because you're taking it away from not a neutral charge, but a positive one. This will be a little bit harder to deposit because rather than depositing it to a neutral plate, you're depositing it to a slightly negative plate. And so it gets harder and harder to move these electrons. And eventually, you get to the point where you have removed all the electrons from here that you can. You've dumped all the electrons you can onto here, one for one. And your capacitor is fully charged. Notice I have closed the switch on the circuit here. So here we have our capacitor fully charged. At that point, you have a charge Q on the plates. Now, it makes sense, I hope, that the charge on the plates would be proportional to the PD across the plates. The bigger the number of joules per coulomb you have here, the more coulombs you're able to move against this increasing charge on the plates. So we say we have Q coulombs on the plates. We don't talk about, you might think that you've got Q here and Q here, plus Q minus Q. We just talk about Q on the plates, right? So we have this proportional relationship, and we can say that Q equals some constant times the PD, and that constant is the capacitance. And the capacitance is defined in terms of this equation. So you can almost make it up. The capacitance of a conductor is 1 farad if the PD across it, PD of 1 volt across it produces a charge of 1 coulomb on the plates. That's the definition of the farad, and the capacitance is the ratio of the charge on to the PD across. So let's define capacitance and the farad formulae. Again, written in red, as I always do, because it's important and you need to know. These are just, 1 markers at the start of your question, but it's important to know. Just like maximum working voltage might be a 1 marker somewhere in the question. You just need to know what it is. So capacitance defined from that equation, the ratio of the charge on a conductor to the PD across it, and the farad, the capacitance of a conductor is 1 farad if a charge of 1 coulomb produces a PD of 1 volt across it, or a PD of 1 volt produces a charge of 1 coulomb. But it would be this way round. The charge would produce the PD. So there are your definitions. So let's look at charge and discharge, because what we have done is we have looked at that instantaneous charging, and that's not generally how we use our capacitor. So we're looking at charging and discharging through a resistor. Here I've added a resistor into my circuit, and let's just examine how this would work. So initially, just after you've closed the switch, there hasn't been time to build any charge on this capacitor. The time, we're saying the time is really, really short. So you have this potential rise here across your battery, and by conservation of energy going from here around the circuit, you'll have a potential drop of V volts. So if we stick a voltmeter in there, we call that VR. We stick a voltmeter in there, we call that VC. At this point, as we've just closed the switch, we have a potential rise of V volts across here. We must have a potential drop across here, but we've said there is no PD across the capacitor. So at the moment you close the switch at t equal to 0, VR will equal V, we call that V supply maybe, and VC will equal 0. That has to equal 0 if that equals the supply PD. So at this point there's no PD across the capacitor, it's all across the resistor. And of course we have a current flowing. We have to have a current flowing, otherwise there wouldn't be a PD across the resistor. But a little later on, you're going to have VR is going to fall because VC will have risen, because you will have some charge on the plates now. So it is getting harder to move those charges, and so the current, the rate of flow of charge is reducing. And then finally, at some perhaps much later point, the current will have fallen to 0. VR, because there is no current now, will also be 0. And VC will equal the PD across the supply. Now, I'm not asking you to remember this, I'm asking you to work this out. At the moment you close the switch, if we take a moment really close to the closing of the switch, there will be no PD across the capacitor because there will be no charge on the capacitor because there hasn't been time to build a charge on the capacitor. Which means all of the supply PD must be dropped across the resistor, which in turn means the current must be at its largest, which also makes sense because as you build charge on here, the current will fall. So at the moment you close the switch, your current's at its largest value. The PD across the resistor is the supply PD by conservation of energy, and there is no PD across the capacitor. But that situation is constantly changing at this point. So as the current flows, electrons are pulled off this plate, dumped onto this plate, and every time you do that, it becomes harder to remove and deposit electrons. And so the current falls. And the PD across the resistor plus the PD across the capacitor by conservation of energy must always equal the PD across the supply. So that's the physics of it. Let's look at the maths of it now. So, sorry. Let's look at the maths of it. So, the graphs then. Well, as we charge, the PD across the capacitor rises towards the supply PD. It becomes asymptotic to the supply PD. We would say it has reached it because it gets really, really close. And the PD across the capacitor, this is discharging graph. The charging graph does this for the PD across the capacitor. If we were to start with our capacitor fully charged and then connect a resistor across it, then the PD across the capacitor would fall exponentially. This is an exponential graph. This has an exponential element to it, but this is exponential. Exponential being that it changes equal proportions in equal periods of time. Exponential growth would look like that. This is exponential decay, falling equal proportions in equal periods of time. You've come across this before with nuclear physics and radioactive decay. So these are graphs you need to be able to sketch. You need to recognize them as well as sketch them. So the PD across the capacitor charging rises towards that supply PD as we discussed earlier. If we were discharging, if we were to connect our capacitor across a resistor, having fully charged the capacitor first, the capacitor would discharge, a current would flow. Initially you'd have that maximum current because the PD across the capacitor is a maximum, but as the PD across the capacitor falls, as the charge equalizes on the plate so that there is no charge on either plate, the PD across the capacitor falls, so the current would also fall because the PD has fallen. If we look at current, well, interestingly, the current does exactly the same thing but in opposite directions. That's no surprise perhaps, but when we're charging, initially the current is as big as it can be because there is no charge on the capacitor, and so it is easiest to move the electrons. But as the charge builds, it becomes harder to move the electrons and the current falls. If you were discharging the capacitor, having charged it as before, just sketch that graph, that circuit for you. So you have our battery. Sorry, I didn't want the battery. Let me just get rid of that. That was not what I intended. So if we have our capacitor and we have a switch in our circuit and we have our resistor, then there will be a PD across the capacitor because it is fully charged. Close the switch, the PD is now across the resistor, so electrons will flow so that the charge that was on the plates, you've got minus Q here and plus Q here, electrons will flow so that there is no charge on the plates ultimately. But as the charge on the plates falls, the PD across the plates falls. Remember, Q equals CV. So as this falls because this is constant. So the PD falls, so the current falls. That's what happens. Sorry, this is the graph. Charging, the current flows in one direction. Discharging, it flows in the opposite direction. So, let's look at the maths of this then. So, for charging, current, we have the current equals our initial current times e to the minus t over CR. This is an exponential equation. Discharging current, we have I equals minus I naught e to the minus t over CR. Now, you might look at this and say, well, this looks very like A equals A naught e to the minus lambda t, doesn't it? Both exponential decay. So you have your time constant in here, and you have a kind of time constant in here. Decay constant and half-life is what I meant to say there. We have a time constant here. Now this is important. This is crucial to how we use capacitors. So let's look at charging potential difference. Well, this is a bit different as we saw in the graph because these graphs looked like that. This graph, of course, looks like that, rising up to that. supply value. So V is V naught 1 minus e to the minus t over CR. So a similar format, but this 1 minus term in there gives us this graph. And discharging potential difference, well, that's nice and straightforward like these. V naught e to the minus t over CR. This is, of course, we're always talking about the PD or the current for the capacitor, although the current for the resistor will be the same, of course, because they're in series. And then because Q equals CV, whatever V does, Q does. So you would have Q equals Q naught 1 minus e to the minus t over CR, and you would have, Q equals Q naught e to the minus t over CR for discharging, because Q equals CV. So you basically have two forms of the equation, this one and this one. And it is charging PD and charging current, that do the 1 minus e to the minus 2 over CR thing. So back to the time constant then. Let's look at that. So if you take your equation, I equals I naught e to the minus t over CR, and you put t equal to CR in, then you get I equals e to the minus 1 times I naught. And that, if you work it out, take it into your calculator, 0.368. So the time constant is the time for the current to fall to 0.368 of its initial value. And so you would have falls to 0.368, and being exponential, 0.368 of that would be the same period of time. So that would be one time constant. That would be one time constant. And of course, if you were talking about the potential difference across the capacitor charging, then it's 1 minus e to the minus t over CR is your factor, which means it's 1 minus 0.368, 0.632. So you could define the time constant as the time for the PD across a charging capacitor to rise to 0.632 of its final value. So two definitions of time constant. The time for the current to fall to 0.368 of its initial value, and of course that is true charging and discharging, so that's kind of handy, that definition. Or it's the PD across the capacitor rising to 0.632, 1 minus 0.368, 0.632 of its final value. 0.368 of the initial value of the current, 0.632 of the final value of the charging PD. You need to know the definition of a time constant. So, we have looked at what a capacitor is. We've looked at what they do. We've looked at what they look like. We've looked at what sorts of devices use them. We've looked at why they do what they do, this buildup of charge. We've looked at Q equals CV. We've looked at the definitions of capacitance and farad based on Q equals CV. We've looked at charge and discharge through a resistor. We've looked at how the PD and current vary for those. We've looked at the graphs of them for current and for PD. We've looked at the equations. for those. And we've looked at the time constant. Two things remain really, some practice at these questions, and I thoroughly recommend you look at your Kerboodle or textbook if you're doing AQA self-assessment questions and check that you can do those. And also the energy stored in the capacitor, which we haven't talked about yet. I'll come back to that in a separate video. I hope that's been useful.